Hello everyone and welcome to this webcast about the new Glasgow-Maastricht AnyBody foot model. I am Sylvain Carbes, I am the presenter today, and I am assisted by my two colleagues Arne Kies and Miol Munayed. The agenda for today's presentation: first, for the new one, we will see very briefly who and what is AnyBody. Then we will ask the question, why a foot model, what's the reason for doing such model. Then we will look at the model itself, how it is done, what's inside. We will do a little bit of validation, a live demonstration, and then we will see the applications, useful applications that we can do with this new model. So the AnyBody modeling system, it's a software for musculoskeletal analysis. It is developed in-house and it is self-contained, so no third-party software needed. It can interface with a lot of other software still, for example with motion capture and image-based data, that's input, for example, for the motion and the scaling. It can interface to finite element software and to CAD software as well. There is an open body model to do the simulations together with the software, and of course this body model has been very widely validated. The principle of the simulation that is done by the AnyBody, it's the inverse dynamic analysis. So that means we use motion and external forces as input, and we get as output internal forces, that's muscle forces and joint reactions, basically. As I said, we have a body model, it's an open model, very detailed, probably the most sophisticated musculoskeletal model out there in the moment, with about 1,000 individual muscle units. It's generic, parameterized and scalable in many ways, and again it is validated. And it covers the entire body. We have upper limb, lower limbs, and the latest addition is the foot model, which is the topic of today. So the new model replaced the old stiff model, and it's now possible to switch freely between the two models. So that was for the general quick introduction. Now we will really go into the foot itself. So first, why did we do a foot model? What's the reason for that? We have joined a project which motivation is to develop foot and ankle orthoses that are personalized for a better fit and better functional performance. So to do that, of course, we need to really study the inside biomechanic of the foot, and for that we require a very detailed and advanced model. This was not the case of the previous foot model we had. It was stiff, and the other foot model we can find in the literature are usually no more than 5 segments, so that's not enough for our purpose. That's why we are coming today with the Glasgow-Maastricht foot model, which is a very detailed model with all the 26 bones of the human foot, the corresponding joints linking the bones, and also intrinsic and extrinsic muscles, and all the major ligaments. The model has been developed by AnyBody technology, and this has been done in a close cooperation with the Glasgow-Caledonian University and the University Hospital of Maastricht. They provided us with very important and helpful data like gait trials and CT scan to construct the model. And they also gave the name to the model, which is now called the Glasgow-Maastricht foot model. As I just said before, this is part of a project, another project which is called the A-Footprint project, and it's aimed at doing rapid manufacturing of personalized insoles. So if you want to read more about it, you can visit the website afootprint.eu. We will now look at the model itself, how it is constructed and what's inside. So it has 26 segments representing all the 26 bones of a real human foot. It has 26 joints connecting all those segments. Those are idealized joints, that mean of the type either revolute or universal or spherical. You can see on the picture below the different bones and joints. That's the colored dots representing the different type of the joints. The data we use to construct the model, it all comes from the literature. So for example, for the joint type, location of the joint center and orientation of the axis. In addition to the joints we have just seen, the idealized joints, we have added some more advanced kinematic constraints. Those are helping to better represent the complexity of the human foot. So for example, we have added lateral contact between some bones. We have that on the tarsal bones, so between cuboid and cuneiforms. That's providing kinetic and kinematic contact. So it also there is also a reaction force between the bones. We have the same type of contact on the metatarsal heads, and we have also added some constraints on the arch curvature. So that helps to keep a natural shape of the foot during the motion. Then we also added, of course, the muscle and ligaments. So all the intrinsic and extrinsic muscles. The intrinsic ones are really the new ones because they were not present in the stiff foot model. This muscle structure is including some very complex muscle structures like splitting and blending tendons. A good example is the muscle you can see on the right picture. This is extensor digitorum longus together with extensor digitorum brevis. So the long muscle is coming down from the tibia as one muscle unit, and then it splits in 4 tendons. And those tendons are blending again with the one of the muscle, the brevis muscle. So that's a quite complex behavior, but we managed to reproduce it using several muscle branches and connecting them at those points and adding some force equilibrium there. Then for the ligament, we have all the major ones, so mainly the plantar ligaments, like the plantar fascia, long plantar, spring ligaments, but also all the ligaments in the tarsal region that hold the bones together here. And again, all the data is coming from the literature. So for the geometry, origin and insertion points, and mechanical properties. This model will be made available soon. We hope to make a beta release in November this year. And together with this, we will include documentation about what you just saw, the joints, ligament, muscles, and reference to all the literature we have used to construct the model. So that was really like the model alone, and now we will see what we need to use the model. So you can see on this workflow chart we need basically 3 things, 3 steps. First we need some patient geometry. So this is to scale the model to the patient we want to study. In the case of the foot, we need either a CT scan of the bones or a scan of the surface of the skin, which is probably easier. Then we need to apply the motion to the model. This is done by a mock-up experiment using the markers. And then we have to apply the boundary condition, the external forces, which in the case of the foot, that's the ground reaction forces. And this is done using a pressure plate. So we'll see those three steps a little more in detail now. First, for the scaling. So it's using the morphing facility of the AnyBody modeling system with the RBF scaling method. More concretely, for the case of the foot, it's using 16 landmarks. So those are landmarks that are placed on the surface of the skin. So we have defined those 16 landmarks on the standard foot, the unscaled one. And then what you have to do is to pick those corresponding landmarks on the geometry of the patient, the new geometry. So that's basically a surface of the scan of the surface of the skin. So you can do that in MeshLab, for example. It's very easy. You just click on the spot to pick a landmark and then save a file with the coordinates. And then AnyBody is doing automatically the scaling with this. So you can see an example of what the scaling is doing. On the right, you can see two pictures of the foot bones. So the upper one is showing before the scaling. The yellow bones are the bone of the foot model, so the unscaled model. And the gray bones, that's a CT scan of the target, so of the patient. So on the upper picture you can see that doesn't match. That's normal because it's not scaled yet. And when the scaling is done, that's the picture below. You can see the two sets of bones, yellow and gray, are matching pretty well. Then we said we have to apply the motion to this foot model. And this is done using motion capture data. So we have developed a specific marker protocol together with the model. That was again in cooperation with Glasgow and Maastricht. It has 28 markers and it has been designed really to cover all the degrees of freedom that are needed in the foot model. If you want to read more about this marker protocol and have the complete definition, you can have it in the paper mentioned below. You can download this paper on the website of AnyBody in the publication list. And finally, we have to apply the boundary condition, the ground reaction force. So this is done using the plantar pressure. Why do we need plantar pressure? It's because if we simply use a force plate like in the usual setup, that's not enough to load all the 26 bones. It just gives one resultant vector and one resultant moment. So that's not enough. We really need a detailed mapping of the force so we can provide it individually to each bone. And this is what the pressure is doing, really. So at the end, we can compute a lot of small 3D forces that are applied all over the plantar surface of the foot. You have the option here to use only the pressure plate or a combination of pressure and force plate. The good thing about using the combination pressure and force plate is that it would give a better accuracy on the friction forces, because the pressure plate doesn't give the friction forces, so it has to be estimated, for example, by estimating the duration of the resultant of the ground reaction force. Whereas if we use the combination pressure plus force plate, then the force plate is really giving the friction, really the duration of the resultant force, and then the pressure is giving the detailed distribution under the foot. Now we will talk a little about validation, which is always important for modeling. We'll see two types of validation. The first one is about the motion. So what we have done here is that we have compared the predicted motion of some joint with the measured motion. This has been measured using bone pins. That was an experiment done by Nestor. So that's the bone pins are a very accurate way to measure the motion because the trackers are really fixed directly into the bone, so there is no skin artifact, for example, no perturbation of the motion. So we took 2 degrees of freedom for this study, the talonavicular flexion and the calcaneocuboid flexion. And if we look at the range of motion, so for example, for talonavicular flexion, we have 9 degrees predicted by AnyBody and 10 degrees measured in the experiment. And for the calcaneocuboid flexion, we have 8.5 degrees predicted against 10.5 measured. So that's pretty good in both cases. And if we look at the global shape of the curve, that also matched pretty well. Another type of validation we have done, it's this time about forces. So we have measured EMG and we have compared this EMG with the predicted muscle activation of the model. So on this graph, you can see the blue curve is the EMG and the yellow one is the muscle activation predicted. And here again, there is a pretty good matching of all the muscles. We have different muscles. We measured tibialis anterior, gastrocnemius, and soleus, for example. This is still an ongoing work, the validation, so those are preliminary results. We're doing more with more subjects and more trials. So there should be more results soon available. Now it's time for a quick demonstration. As we have done a lot of theory, now we'll see a bit of practice with the software, really. So this, you can see now the AnyBody modeling software. So for the ones that doesn't know it at all, we have several windows on it. So this, for example, is the main window with the script. Everything is done via this special script language we have called AnyScript. Then we have a model view window where we can see the model. So here you can see the leg model and the foot model attached to it. If I zoom a little bit on the foot, you can see all the different bones, the muscles, and the ligaments. The ligaments are in white, for example. So now we'll launch the simulation. It's in fact a replay of the simulation because the simulation in itself takes several minutes, so to make it convenient, the replay is faster. So you can see the model moving. It is driven with motion capture. You can see the markers on the leg that are providing the motion. I will play it again so we can have a look also at the forces. You can see all the small blue vectors on the plantar surface of the foot. These are the forces we apply using the plantar pressure. And you can also see some muscle activation, for example, the gastrocnemius here, that is bulging. So when the simulation is done, we can investigate some results. This we can do using the chart window. So on this one we can access really all the output of the model. There is really a lot of output. We will not see everything, but quickly we can look, for example, at the muscle activation and forces about all the individual muscles. We can also look at the ligaments, for example. So this, what you can see now, is the force inside one of the branches of the long plantar ligament. We can also look at the joint. So it can be joint motion, but also joint reaction force, for example. So this is the reaction force on the joint between the first metatarsal and the medial cuneiform. So the red curve is the compression force, and the blue and green curve, this is the shear force in the other direction. And you can find result, like in this case, for example, the peak compression force on this joint for the stem phase, it can be about 800 newtons. So we can have this kind of information and much more. As I said, I will not show everything now. So I will go back to the presentation and go on with it. And so now we will look at some application, what we can really do with this model. So one of the most classic, I would say, application, it's providing a patient-specific finite element load case. So this is something we have been doing for some time in AnyBody with other body parts and other bones. For the hip joint, the femur bone, for example. The new thing is that now we can do it for specific parts of the foot, detailed parts of the foot. So, for example, I choose today the case of the calcaneus bone. So, concretely, the workflow is the following. We have some patient information, so that's a CT scan of the bone, so we can scale the model exactly to the patient. Then we have an activity of the daily living that we want to study. We want to get the loads for, so that can be walking or running. So that means we need motion and pressure for this activity. Then we put all that in the model, run the inverse dynamic, and we can export the load case to the finite element software. So that's really export a detailed load case, because it includes, in the case of this calcaneus bone, that would include the load of the ground reaction force, the forces of the muscle on the origin and insertion points, the forces from the ligaments, and also the forces from the joint reaction force. So it's a very complete and in vivo-like load case that we can provide. If you want to see a little more about how it generally works, this workflow, it has been presented on a previous webcast. You have the reference on the bottom of the slide. It's called the new release of the AnyBody modeling system version 5.2. So that was done in June, and you can find it in our website on the replay section with all the other webcasts. That was one concrete application. There are many other applications you could do with this model. It could be in orthopedic and surgery. So for fracture fixation plates for the joints. It could also be used for studies about shoe and insole development. Also for pathologic foot, not just healthy, but it could be flat foot or diabetic foot. You could get info for orthosis, ankle and foot orthotics, all kind of exoskeleton and gait applications. Now if we look a little bit in the future and the work in progress, so I said several times the motion comes from the mock-up experiment, and we are working now on an alternative way to provide the motion, which would be using plantar pressure instead of the mock-up experiment. The motivation behind that is that well, to do a mock-up experiment, you need a lot of material. It has a certain cost, takes time and space, so not everyone can do it. Whereas pressure plate is much easier, so that would be a much easier, faster and cheaper way to run the model. And we can use plantar pressure to get the motion because it gives already a lot of information about the timing, the heel strike, the heel roll, also how much the foot is going down during the stand phase, etc. So you can see now a video about the work we've been doing in this direction. So we are already able to drive the leg and the foot using just the pressure to generate the motion. So it looks already pretty natural, and it's pretty close to what the motion that we would have with the markers. So that's, again, it's still work in process, so it's not finished. We still have to do more validation and more experiment on it. We are already reaching the end of the presentation. So if we try to do a small summary of it, we can say that we have developed a new foot model, a very detailed foot model, including the 26 bones of a human foot, the corresponding joints, and all the muscles and the major ligaments. This model is providing very detailed biomechanical information on the inside of the foot, and we hope to make a beta release in November this year. We have done some preliminary validation, and that gives already good results. And we have a very wide range of potential application with this model in shoe development, insole design, orthotics, and orthopedics. So this is the end of the presentation. Thank you very much for attending this webcast.